Let's go ahead and enumerate some of our kinematic assumptions. The first is that the cylinder length stays unchanged. Now, I don't think we put in a label for that, but we can just call it L for right now. So, in other words, it started at L, it's going to end up at L. Secondly, the diameter was originally 2c in length, and we're going to say that that straight line diameter stays straight and unchanged in length. Oh, haven't been spelling long. Stays straight and unchanged in length. So in other words, if we look at the end face, it started off at a distance of 2c and it's going to end at 2c. The third is that the flat end face so our flat end face, so the end, I'll just call it the end face for right now. End face remains flat. There is no warping, there is no twisting. So what's happening if we combine all these together is the original straight line diameter was dashed and it ends up here. So it was straight across and then it rotates as it goes through that angle. And that then is going to be our theta. So those are the three primary kinematic assumptions that we're going to make for this particular cylinder. And if you think about it, that is the simplest possible way that it can deform that really is not going to defy some sort of basic physical principle. So let's sketch what the consequences of that are going to be. Here's our undeformed solid. Sorry about that. And I'm going to go ahead and draw a length down this way. There it was at the original, and then there is my original radius, the outer point C. And then I'm going to draw it after deformation, so it goes down like so. Now, we're going to go ahead and assume that this end is going to be fixed. So we're going to fix that end and let the other one rotate. So what happens, that straight line length then basically moves down to here, like so. So there is the deformed path of a particle at the outer radius that we've got here. So again, that distance is going to be c. This is going to be theta. Let's draw that one more time looking at the end face. So it was here, and then it rotates down to so. And that is our angle of theta. This is our distance c. And remember then that this is going to be L. So really, everything is just moving as a bunch of straight lines. The diameter moves as a straight line. The outside edge moves as a straight line. Now, we notice that this line was originally straight, and now it's going along a curved surface. But the angle is so small that it's really not going to be much of a deviation from a flat line. Well, now notice what happens. Now we were originally at 90 degrees. So this made an angle of 90. But now notice what's happened. There's going to be an opening up of that 90 degrees. So what was originally 90 on the outer length of the circle is now going to be a little bit bigger than 90. And that is our change in angle between two lines that were originally perpendicular. So that's going to be our shear strain. So this is gamma at the outer radius C. So this is the shear strain at the outer radius C. And that's gamma. So again, drawing this one more time, I'm looking at the side of the cylinder. There was the original length, and it was originally at 90 degrees. But now it's opened up a little bit. If we were to use our sign convention, which we won't bother with right now, that would be a negative because it's making my thumb and my finger hurt because it's opening up a little bit more. Now what we're going to do is we're going to focus on this radial distance here. That arc length is going to be the key measure of deformation. And we have two ways of getting it. So notice that this arc length, and it doesn't matter really what we call, we're only going to use it one time. We could call it L sub A is equal to the length of that arc. That is a completely ad hoc designation. You could have called it A sub L. It doesn't make any difference. So the length of the arc that we've got there, that's a circular segment. I can get that either by multiplying theta by c. It's just going to be c theta. That's one way of getting it. Or I could also use from this side, I could sweep through that angle multiplied by L. So that's also going to be equal to the shear strain at the outer edge multiplied by the length. So I can eliminate this guy. I'm not really interested in that. And I've got this intermediate result that c theta is equal to gamma c times L. Now, at this point, the only things that we know are L. We know that length of the segment that we care about. And we also know C, the outer edge. So that guy we know. This we know. We do not know theta. We do not know the shear strain at the outer edge. But that's okay. This is very common in mechanics. We work our way through the analysis, and we're probably going to introduce some variables that we don't know, but we keep moving. We use what we know, and then eventually we're going to be able to close the loop and figure out what all those are going to be. All right, so that is our first expression. Even though it really doesn't have some of the parameters that we care about, we do care about theta, obviously, but it's going to be a nice intermediate result for us. All right, now the second thing that we're going to do may look like it's going to not make a lot of sense. We're going to actually go inside of our original cylinder and take out a smaller cylinder. So now we go inside of our cylinder and focus on a smaller interior cylinder. Now I'm going to try to represent that visually by taking our original one and going like so. But now I'm going to go on the interior, on the inside, and carve out a solid one. It looks like this. There we go. It still has a length of L, like so. And I still have, there's my end face, and here is my interior one. Same kinematic model. It was here, and now it's here. So that angle is still going to be theta. But now we're going to let the radius of this inner one be rho. So the radius of our interior segment then is going to be rho. Now, you might be used to dealing with r, but for whatever reason, rho, the Greek letter rho, is kind of the traditional variable to use for this particular sort of analysis. So now what we're going to do is similar to the same thing, similar to what we did earlier. And by the way, we still have this one segment that looked like this, and now it's going to end up, I'm going to try to draw it here like so. There we go. So that was the original, and now we're up at here. So now notice we've got this arc segment, that like so, and then that's going to be the same as this inside here. And now notice that that is the opening up of that long line along the diameter, along the length of the cylinder. And that angle we're going to call the shear strain. That is a change in angle between two lines that were originally perpendicular. But now we're going to call that gamma at rho. So that's the shear strain at a radius of rho inside that little interior diameter. So now our second, let's call it something like L prime, at rho So that arc length, that's this distance right inside here. That is equal to the length of the interior arc. And I put the prime there just because it says it's after the deformation, even though the other one did earlier as well. But that can be measured then by two combinations. I can either say it's going to be rho times theta from this, so that's going to be rho theta, so I'm going to get this circular segment from the end face, or I can sweep the shear strain at that radius rho multiplied by the length. So again, that lets us eliminate that value because what we've done is we've matched our two kinematic variables of rho and gamma at rho. So we've examined what happens using our kinematic hypothesis, what happens to our variables, what is the link between gamma and the shear strain. So now we can combine these. Notice we've also got C theta is equal to gamma at C times L. Now what we're going to do here is we're going to go ahead and isolate from both of these. I'm going to use this expression to write that theta divided by L, and that's going to be equal to gamma at C divided by C. But we also have, from this expression, we have theta divided by L is equal to gamma at rho divided by rho. So now we're going to grab this. That is a key relationship, and we're going to write gamma at rho, and that is the shear strain at any radius rho, and that's going to be equal to rho divided by C times gamma at C. So that is gamma at rho. And that is a big, big result for us. This is huge, and because it basically says that the shear strain varies linearly over the cross section. So shear strain varies linearly with the radial distance rho. Big result, and that closes out our part B.